All right, let's get started. So we're very happy today to have Donghui Jeong today. He started his career in Korea, in fact. He's from Korea, North Korea.
South.
South Korea. That would be amazing. And after that, he went on to the University of Texas to work with Ichiro Komatsu as a grad student. After he graduated, he went to Caltech to work with Mark Minkowski, which he followed to Johns Hopkins, which I guess was a smart move. And after that, he went to become an assistant professor at Penn State. Go ahead. He's going to tell us about HETDEX.
Right.
Which might or might not give us HETDEX.
No headache, I hope. Okay, thank you for the invitation. So I'll talk about the Galaxy survey that I have been working for about 10 years, since day one in my grad school. That's HETDEX. That's the acronym for Harvey Everett Telescope Dark Energy Experiment. We haven't started the survey yet. The survey will hopefully be started at the end of this year. And this is a multi-institute collaboration. So Central Institute is the University of Texas and McDonald Observatory, where the telescope is. And then Penn State and Texas A&M are US institutes. And then there are German Institute, MPA, LMU, AIP, MPE, and Göttingen. And we also have health from Oxford. So I'll mostly talk about my contribution to this survey, the cosmology with the survey. And here are the list of people involved in the survey. What I like about this survey is that we have only a handful number of people. It's not like a Planck or Euclid. And then having collaboration meeting for 10 years, we're all good friends of each other. It's a very friendly environment to work in this survey. So first, let me introduce the goal of this survey. So let me bring you back to the Decadal Survey 2010. In the report from the Cosmology and Fundamental Physics panel, they highlighted 4 questions that we are good to address in this decade. They are, how did the universe begin? Why is the universe accelerating? What is dark matter? And what are the properties of neutrinos? If you look at those questions, they are all related to the constituent of standard lambda CDM models, the origin of inflation, dark energy, dark matter, and neutrino mass. I'm trying to convince you in this talk that I can do I can address all of these questions by using the data from the HETDEX survey. So what is HETDEX? So the HETDEX is, as I said, Harvey Everett Telescope Dark Energy Experiment. That is the first blind spectroscopic large-scale structure survey. Blind means that we don't pre-select any object that we'll observe. So we just put the fibers in the focal plane, get all the light that we can get. And second is the first 10 gigaparsec cube class survey, a high redshift. You're targeting the Lyman alpha emitters at redshift 1.9 to 3.5 with sufficient number density. It's number density-wise, it's comparable to Sloan, both. So as you know, the 2DF, Sloan, Wiggle Z, they're all focused on the low redshift and G redshift less than 1, but we are at high redshift. So this is really a Texas-sized survey. So I prepared some of the Q&As for you. First, how big is the survey telescope? It's a 10-meter class telescope, the third largest telescope in the world. Actually, it's 9.2 meter. And whose telescope is that? And telescope is actually in McDonald Observatory in West Texas. And then third question is crucial. How many spectra do you take for one exposure? So we put 35,000 spectra at once and get the light from there. And then people ask me, are you not wasting lots of fibers? And that's true. We are wasting a lot of fibers. But we believe that this is the only way we can find something very, very new. That's actually one of the exciting things about this survey. Beyond what you're expecting from the survey, we'll truly, I hope that we get something very, very new from the high redshift object. So this is a one-page summary. HETDEX will use 10-meter telescope to get the Lyman alpha emitting galaxies at very high redshift and get information about cosmic acceleration right now. So spectral case. So HETDEX will use something called VIRUS. VIRUS is an acronym for the Visible Integral Field Refractive Unit Spectral. It's IFU. I'll explain what IFU is in a moment. We'll put the 78 units of IFU. Each unit has 448 fibers. If you multiply these two, that gives us a number that's 35,000 fibers in the sky. So here's how it looks. So I took this picture in Potsdam, Germany. So there are two ends. So there's one guy whose job is winding these optical fibers. And then you wrap this thing with this cable. And at one end of this fiber, we have this two-dimensional structure that we'll put this in the focal plane. On the other side of this fiber, we'll align each of the fiber at this 2D plane to this 1D. And in the CCD, we'll disperse this light into this vertical direction, right? So if you look at this thing in the DS9, x-axis will be your wavelength, and y-axis will be your position in the sky. That's how you get the multiple spectra at one exposure. And that's a testing that we did. So I use iPhone to emit the other side of optical fiber just to check that this thing actually works. So this is how it looks. That's an artistic view of this HETDEX setup. So here is the HET, and this is the tracker system with a wide field corrector here. And then we connect the optical fiber from here all the way down to here, and this is our detectors. And we have cryogenic system, and 78 units of these guys are located here. And that's the zoom up of this upper part of telescope. We have this tracker and wide field corrector here. And that was still artistic view, but then this is a real one. So last year, the big giant trucks were at West Texas, and we installed this tracker. So this telescope, the survey is making some progress. And at the moment, we had some trouble with a wide field corrector. We cracked this thing as of last month, and we are now trying to figure out how to get the correct mounting and the correct alignment in the optical system. That's the status of survey as of now. So we hope that survey will really start at the end of this year. So here is the survey footprint. Here are the regions of Sloan. And we have two fields. Our spring fields is here, and our far field is here. Spring field is about 300 square degree for the nominal 3-year mission. And if you extend it to 5 years, then you have additional 130 square degrees. And the far field is 140 square degrees for the 3-year mission. And if you extend for 5 years, then you have additional 84 square degrees. In terms of sky coverage, it sounds really small, but because we have the high redshift, we have a longer arm. So if you calculate the volume enclosed in this tiny area, we get 9 gigaparsec for the 3-year and 13 gigaparsec for cubic for the 5-year. It's a huge volume. And each one of the survey area, we cover this with a telescope. Each circle here represents the position array DAG of telescope field of view. So one exposure field of view is about 22 arc minute, and we'll have about 4,000, I call it shots. Shot is like one telescope position here. And each of these positions is filled by IFU, integral field unit. But because we only have 78 IFUs, we cannot fill the whole field contiguously. Instead, we decide to make one pattern like this. So that's a 78 IFUs here. And then each one of these square is filled with the small optical fibers. So we essentially observe everything inside of this square, but we don't observe anything in between those squares. But this is okay because we are targeting the BAO and large-scale structure. So inter-IFU distance here is about 1 megaparsec. So, but if you are chasing after 100 megaparsec feature, then this thing should not make much of a problem. You may wonder why we have this hole here. This hole is reserved for another instrument. This will make slight complication in the study of window function, but as a whole, I show that it doesn't make a big problem of detecting BAO. Okay? So what do we detect? We will detect Lyman alpha emitters. Our wavelength range is about 350 to 550 nanometer. And then our resolution is about 700. That's a lambda over delta lambda. And the flux sensitivity is about 10 to negative 17 erg per centimeter square per second. So that will give us about 0.8 Raman alpha emitters at ratio 1.9 to 3.5 and 2 million O2 emitting galaxies. I'll tell you more about it in a second, but this thing is a little bit unfortunate thing because Raman alpha emitter at 1216 at high redshift can be confused by O2 emitters at 3727. So you have to invent a way to distinguish them. So one way to impress you is that so far we only know about 1,000 Raman alpha emitting galaxies. But if HETDEX starts observing, we overcome this number just by 2 hours of observation of full HETDEX. So that will be a very interesting thing to look at if you're interested in Raman alpha emitters. So that's the one example LAs, because I told you that we have prepared this for this survey for 10 years. So we have 1 unit of IFU, and then we put this 1 IFU to the 2.7 meter telescope, and then we did detect LAs. That's a typical spectrum of LAs. We have pretty much nothing elsewhere, but we do detect some broad line, some bright line at one location. This particular LA is at redshift 3, and this is how it looked in the DS9 IRAF. And then we detected about 105 LAs at this redshift with this field of view. The number 0.8 million LAs is just extrapolating this value from 2.7 meter to 10 meter class and then having multiple IFUs. So our estimation of this number density is pretty robust in that sense because we had these prototype surveys before. And then we also detect others. So that's the place that I'll tell you about O2 emitters. In this pilot survey, we detected 397 emission line galaxies. And then there are O2s. So that's emission line galaxies, and we have 105, I said LAs, that's confirmed by other surveys, but then we have like about 300 of O2 emitters, right? Studies so far suggest that O2 emitters are normal emission line galaxies, and they have larger continuum. So continuum to line ratio, or equivalent width, must be bigger per LAE and smaller for O2. So our rule of thumb is that if this thing equivalent width is greater than 20, that might be LAE, and less than 20, that might be O2. But this is not perfect method, so we are now inventing a better way of distinguishing Raman alpha emitters from O2. But our goal is that to take this contaminant ratio to less than 1%. But that's one current challenge that we have in the survey. So as I said, prime goal of the survey is detecting the angular diameter distance and the Hubble expansion rate at redshift 2. And we have subprime goals or other prime goals that we kind of want to address this question, like is the observable universe really flat? And the forecast that HETDEX can tell the omega curvature to 0.1% level is simply because we are at the high redshift, and as you go to higher redshift, the curvature make the bigger difference than low redshift. That's why you can detect curvature better than other surveys. And you can also detect the neutrino mass. I'll explain in more detail later, but then the current survey design says that if neutrino mass is greater than 0.1 electron volt, then you can surely detect it with about 3 to 4 sigma sensitivity. And that the galaxy survey is detecting neutrino mass is getting tighter and tighter, so soon will be the regime that we can for sure detect some mass. So the neutrino oscillation experiment tell us that neutrino mass must be greater than 0.05 eV, so we'll cross that limit soon. And then also we'll also answer the question of origin of universe, that the inflation predict that the single field inflation predict that there's the so-called FNL, local time non-Gaussianity, must be very small. But then Now Planck detected it with delta FNR of about 5, but with this survey, I can measure this thing with a bit smaller uncertainty than Planck. And then also we can measure the primordial power spectrum shape with delta NS of 0.02, and then the running index to 0.05. That's the exact.
So the constrained delta NS of 0.025, and what is Planck? Isn't that already in that range?
Oh, I don't think so. If you look at this Planck plot of R versus NS.
This is 1 sigma, no?
Right, that's 1 sigma, yeah.
I don't know. I thought it was already.
That depends on what are the parameters that you're looking at, right?
Yeah.
And the subprime goal is that because we are doing the blind survey, we really expect to see something completely unexpected. And also we'll detect the white dwarfs and metaprostars and this distant cluster of galaxies, but those are the subject of other persons, but not my main thing. So let me start talk about large-scale structure. So this is the, as you see this multiple times, this is the map of large-scale structure observed from Sloan Digital Sky survey. Here the blacks are main galaxies and red are the LRGs. And if you look at this figure, this is nothing like a random. That is what we call large-scale structure. Right? Large-scale structure is, in a sense, measuring how much of this distribution is different from random, right? And then how they quantify it, we use the correlation function and the Fourier analysis. There are two things, 2-point correlation functions and power spectrum. Those are the now working horse observable from these galaxy surveys. And 2-point correlation function is the excess number of pairs beyond the random at separation R. So if you just pick up one galaxy and count the number of neighbors as a function of R and ask yourself how many more galaxies or less galaxies you detect in the survey is your correlation function. And in mathematics, this is same as correlating one delta to another delta at the two different separations. Here, delta is the density contrast. Is the excess number of galaxies beyond the mean. So you divide by mean and subtract 1. If you go to Fourier space and going to Fourier delta of, instead of delta of x, you have 2 delta of k, then you get the power spectrum. And how does it look? This is a measured 2-point correlation function and power spectrum. This thing will pops up in this talk. And correlation function, we measure it as a function of the distance, separation between two galaxies. And power spectrum, we measure this in terms of wave number. So big wave number means smaller scale, and small wave number means large scale. And first, let me tell you about how do we get the information about inflation. So inflation gives, it happened at a very early time of the universe. It gives the initial condition. And from here to there, gravitational instability act, and then small fluctuation here is amplified to eventually form a large-scale structure we observe today. And if you look at this thing in the linear power spectrum, so this line is the initial matter power spectrum. But then because of this gravitational instability, later linear power spectrum we observe today is this shape. And then we know exactly how to go from here, simple power law initial power spectrum, to this observed linear power spectrum. If you know omega matter, omega baryon, and H. And then these numbers can be measured from CMB studies. So if you measure this guy, then you can invert it that as by means of transfer function, and you can measure the slope of initial matter power spectrum. So that's how well you can do it with the HETDEX. So these are the Planck uncertainty value. And then with HETDEX, on large scale, you don't gain much of information because Planck already measured the large scale initial power spectrum very well. But as you go to smaller and smaller scale, HETDEX can add on some information on the measurement of initial power spectrum. And also, if you go to very, very small scale, now you can talk about measuring alpha S. So alpha S, the running of primordial tilt, means that you need to measure primordial tilt at 2 different k number. That's the way that you can detect the derivative of a tilt. So if you can measure the power spectrum of the k of 0.3, that's what you can do. Then you can also measure the running index. In the context of Planck, I think Dan asked this question. Then this is a Planck 1 sigma and 2 sigma contour. And then by adding the HETDEX information, you can shrink this thing to this blue line.
0.002.
Yes, I guess is the point. Yes.
That number was a big one.
Yeah.
Oh, really?
Yeah, I think that was the point.
Okay.
Yeah.
Sorry. Right. I see.
Yeah, it's next to 0.
Okay, I missed that. And then, but HETDEX, we can detect some signature of primordial gravitational wave, but we are not as competitive as Planck. So this vertex line is just this line is just vertical. And then here we have this wiggle in the linear power spectrum that is so-called BAO. And BAO is already you know this thing, right? You know what it is. So this is the fluctuation map of CMB, and we have hot and cold spot here. And then in this map, as you know, we have one length scale hidden. The length scale is acoustic scale. It's very hard to see this, but then it's easy to see if you stack this image around the cold spot and hot spot. That's the map. So that's real data. So if you stack all of these fluctuations around the hot spot, this red dot, and cold spot is blue dots, that's what you get. And around this cold spot and hot spot, you have very nicely defined the ring structure. This is about 0.6 degree. That's so-called a sound horizon size. And from the CMB study, we know that this sound horizon size is about 150 megaparsec. And then I just tell you that this sound horizon is occupied 0.6 degree on the sky. If you know this length, if you measure this, you can calculate the angular diameter distance, right? That's the way that we constrain this one number from CMB. The exactly same thing happens here because this acoustic signal is in the harmonic scale, and that signature is in the baryon photon plasma, but later baryon decoupled from the photon and coupled to dark matter, and the exactly same kind of oscillation is imprinted in the matter power spectrum, right? And using this, we measure distances. So we know that DBAO is about 150 megaparsec from CMB, and we measure angles subtended by this DBAO, and redshift difference correspond to this DBAO. And then redshift difference and angles subtended by this DBAO is related to the angular diameter distance and Hubble constant at high redshift. That's what we are measuring. Then we know this value from CMB. Then we measure dA and H. And dA and H are related to dark energy equation of state and the energy density. That's the way that we can detect dark energy properties from this geometrical test. But people talk about this BAO a lot, but we can also use the full shape of power spectrum to get additional information about this dA and H. The principle is simple. In the galaxy survey, for any given galaxy, you measure 3 numbers, RA, DEG, and redshift, right? If you translate this thing to the power spectrum, you always have to assume some fiducial dA and Hubble constant, right? Therefore, the assumed dA and assumed Hubble constant will change your observed power spectrum, right? But then you know the shape of real power spectrum, and then changing dA and H is corresponding to just shifting your power spectrum left and right in the Fourier space. So you shift it until you match the expected power spectrum. That's the way that you can get additional information on dA and H from the full shape of power spectrum, not just using BAO. So if you use this full shape of power spectrum, your error contour is shrunk by a factor of 4. So here is the error in dA and H, the 1 sigma and 2 sigma. If you just use BAO, there's a large ellipse. And if you use a full shape of power spectrum, you get the small ellipse. And you can also notice that the axis of principal principal axis is shifted from here, dA squared times h is constant, to dA times h is constant, right? This is because we add additional information through so-called Alcock-Paczynski test. Alcock-Paczynski test is, in its original form, is as following. If you know a object, you don't have to know the size of the object. If you know a object, and if you know the fact that this object is spherically symmetric, then you know that this vertical length must be the same as this horizontal, vertical to line of sight length is same as the line of sight length, right? Then you can, but then this side is your angular diameter distance times the angle subtended by this, and then this side is related to your redshift difference divided by h. But because you know the fact that these two are the same, you can equate them. And if you equate them, and then you can massage this equation so that the observable side in the left-hand side and cosmology is in the right-hand side, means that your observable delta z over delta theta can give you the information about dA times h, right? But then later, people realize that you don't have to know the fact that this is exactly spherically symmetric. Any object, you know the shape or the angular shape of this thing, you can apply this technique as well. In terms of power spectrum, in the parallel directional and perpendicular directional K number, if you know the shape of this contour in the galaxy survey, for sure, then you can do the same kind of test because your K perpendicular to K parallel is always proportional to dA times h, right? In other words, let's say you have some object that you know the shape in the K parallel and K perpendicular direction. So if your dA is wrong, then this shape will be elongated into this direction because dA will be responsible for the perpendicular directional shape, distance. If your h is wrong, you may elongate this thing to the line of sight direction because h is responsible for the line of sight directional distance. But if you're wrong for both dA and h, you can still get the same shape, right? That's the way. That's the reason why we get the dA times h constraint by knowing that the angular dependence of this function, the power spectrum in K space. So let's put the HETDEX into context of current best constraint. These wide contours are from the Lyman alpha observational boss. And then this error bar is big, but the HETDEX measurement of dA and h is so good, then you can shrink this big contour to this small ellipse. So that's something that we are really looking forward to in terms of dark energy constraint, right? And third, I'll talk about neutrino mass. So now temperature of CMB is 0.2 millieV, and you know the temperature of neutrino is about the same order. But then, as I said, neutrino oscillation measurement state that mass of neutrino must be bigger than 0.05 eV. The neutrino must be massive right now. Right? How does massive neutrino do to the structure formation is summarized in this plot. Here, y-axis is a K, so small scale and large scale. Axis is a cosmic time. And I show here one line. I think you should just focus on this curve. And this is a time for this particular mass of neutrino. I just put in the plot. So this is now here. Neutrino were relativistic at early time. And there was a transition epoch. And after this transition epoch, neutrino become non-relativistic. And here this line is the neutrino Jeans length, or the Jeans wave number. So structures can grow only for K, which is bigger than the Jeans wave number. So neutrino fluctuation can grow only here, right? Because at early time, neutrino Jeans horizon is about the same as a cosmic horizon. There's no scale that neutrino can grow. So the effect in the power spectrum is suppression of power. So there is a transition epoch, this K number. But then it was on the small scale, you do see the suppression of linear power spectrum compared to a zero neutrino mass case. And then when neutrino mass is 0.13, you will see that about 7% suppression in the scale of k of 0.1. This kind of thing can be detected by 3 to 4 sigma significance from the HETDEX survey. And then this 7% suppression factor is related to total neutrino mass budget in dark matter. And then this mass budget, omega neutrino, is related to total mass of neutrino over some number. So if you detect this suppression factor, then you can measure sigma m neutrino from the galaxy survey.
Does that change a lot from recombination to redshift 2 to 7%?
What do you mean? This 7% is in the linear power spectrum right now?
So it's already there at recombination.
Oh, no. You don't have that in the recombination. Right. At recombination, neutrino were still relativistic. So there's no transition epoch. So if this thing happens, this power spectrum, I think you can think of it as some linear power spectrum after this transition epoch. That depends on the mass of neutrino. And then HETDEX can also detect the primordial non-Gaussianity. So Gaussian random field can be specified by power spectrum, right? But then if you have non-Gaussianity, that means that you have something beyond the power spectrum. So usually we parameterize the non-Gaussianity by using the bispectrum and trispectrum. And because of statistical homogeneity of universe, this bispectrum always come with this delta function, and trispectrum always come with this delta function as well. And then this delta function means that bispectrum is non-zero if and only if this K1, K2, K3 forms a triangle. And trispectrum has the same story. And then why do you detect non-Gaussianity? Why do you want to detect non-Gaussianity is because of this consistency relation. The first consistency relation due to Maldacena states that FNL from the plain vanilla single field inflation model must be this. And if you plug in 0.96 to NS, and this means FNL must be 0.017 if inflation is driven by a single scalar field. And there are second set of consistency relation saying that the tau NL, which is the amplitude of this collapsed 4-point function, must be greater than 6/5 of this FNL square. So the implication of that two theorem is this. If you detect FNL greater than 1, that will rule out all single field driven inflation model. And then if you detect this thing, but not detecting tau NL, and they can possibly rule out both single field and multi-field inflation model. That's a big motivation of chasing these two numbers. But so far, those are the current best constraint. FNL is from Planck. You have 2.7 plus minus 5.8, so it's still constant to be 0. And FNL from large-scale structure, like Sloan's Sky survey quasar power spectrum, gives 31 plus 16 minus 27, so that's still consistent to be 0. And tau NL, we don't detect anything, so inflation is okay. But then from the future galaxy surveys, our aim is to make this constraint tighter and tighter. So how does that non-Gaussianity affect large-scale structure? So this is a plot. I took it from the Dalal et al. And they run embodied simulations with positive and negative non-Gaussianity. So this is a Gaussian case. There's FNL 500, 5,000, and negative 500, negative 5,000. If you look at this cluster region, if you increase FNL, it gets brighter and brighter. If you increase FNL to negative, it's less brighter, and you don't see a cluster here. Right? So same story for void. But void gets more and more apparent if you have negative non-Gaussianity. So essentially, the effect of non-Gaussianity on large-scale structure is that this FNL scales the local variance of density field. Let's say we have this cosmic mean, the fluctuation around the cosmic mean. If you put this fluctuation to the overdense region with positive non-Gaussianity, if the galaxy field, density field is Gaussian, large scale doesn't care about small scale. You just add this black line to this blue. That's what you get for red. But then if you do have non-Gaussianity, on top of that, this non-Gaussianity will make the variance of fluctuation bigger. That means that you rescale this difference to the bigger variance. So fluctuation amplitude is bigger. The opposite thing happens for negative non-Gaussianity. If you have Gaussian case, you just add up this blue to this green, this blue to this black. That will give you red. But because of non-Gaussianity, the underdense region fluctuation will get shrunk, and then you get the blue. So we'll have less structure in the void and more structure in the overdense region. That's the general prediction of non-Gaussianity. And then this will give us this power spectrum. So this is the Gaussian power spectrum, Fn at 0. And if you have Fn at 50 and 100, and then you do see the difference on the large scale. And then that we parameterize this thing in terms of scale-dependent bias. That's a Gaussian linear bias plus the scale-dependent bias that is scaled as 1 over k squared and then proportional to FNL. And that's the way that we can detect this signal. Because this signal is apparent for the large scale, we want to measure the large scale power spectrum correct to get this. But there's one caveat though. The similar effect can happen on large scale because of general relativity. So for each galaxy, what you're observing is RA-DEG redshift. After we observe the galaxy using RA-DEG redshift, we chart this galaxy based on our best fit cosmology model to the point that is dictated by the observed direction. But really, what we have to model is the trajectory of photon, right? The photon from galaxy is deflected due to the metric perturbation along the line of sight. Therefore, our charted galaxy position is distorted from the real position of galaxies, which is here. And this difference can be modeled by including Sharp-Wolfe effect, Shapiro time delay, and all the other effects due to the gravitational potential. And then because this effect is due to the gravitational potential, this shift will induce a similar signature of non-Gaussianity. As an example, for HETDEX parameter, I use bias of 2 and redshift 2.7. This is a Gaussian power spectrum. And there are two lines actually here, the thick solid line and the dashed line. The one is Gaussian power spectrum with the GR effect, means that relativistic correction due to gravitational potential that rises at small scale because gravitational potential has 1 over k square factor compared to the matter density contrast. And this GR effect can be mimicked by FNL of 0.7, right? So even though we don't detect anything from the galaxy survey, we still expect to have some signal on large scale that is similar to non-Gaussianity of 0.7, just simply because the light path is deflected from the straight line. And for many various of bias parameter and the survey redshift, we calculate this effect, but then GR effect is in the ballpark of FNL of order 1 for the many surveys. And measuring non-Gaussianity from the galaxy survey for HETDEX using this power spectrum technique that you're looking at the large scale deviation, we get the delta FNL of 20, but using the bispectrum, then you can get the delta FNL of 3.6. Even go to the futuristic survey with a huge volume, 100 gigaparsec cube with 100 million galaxies, we get the delta FNL of 3 per power spectrum and delta FNL of 1 from the bispectrum. Why is bispectrum so good? The reason is because from the bispectrum, we can disentangle the nonlinear gravity effect from the primordial effect. So what makes the bispectrum? The galaxy bispectrum consists of many signals, but I can classify this signal by two categories. First one is a low redshift, say foreground, in terms of inflational signal measurement. The nonlinear matter clustering can generate the non-Gaussian signature on top of Gaussian one, and nonlinear bias also does the same thing. Nonlinear redshift space distortion. These three things can make the non-Gaussian signal out of Gaussian initial condition. But there are two contributions from the primordial part. So primordial bispectrum can generate the bispectrum in two ways. Linearly evolved non-Gaussian mirror bispectrum can generate the observed galaxy bispectrum. And the scale-dependent non-Gaussian bias, the same sort of delta B that I described in the previous slides, can also generate a non-Gaussian galaxy bispectrum. So I showed the shape of this bispectrum in this plot. Here, I assume that K1 is the longest side of triangle, K2 is middle, and K3 is the smallest one. And then I draw this thing. X-axis is a K3 over K1, so that goes to 0 to 1. And Y is the K2 over K1, goes from 0.5 to 1. And this triangle is the triangle that satisfied all the condition. And here A is the so-called squeeze triangle when K3 is very, very small and K2 and K1 are about the same. And E is the equilateral triangle when K1, K2, K3 are all the same. And C, I call it folded triangle when K1 is the longest and K2 and K3 are equal. So here are the signature of Gaussian terms. Gaussian terms means that even universe start from Gaussian initial condition, but nonlinear evolution of gravity and bias can generate a non-Gaussian signature, which is encoded in the bispectrum. In that case, I show you for two K1, so small scale, large scale, and a little bit smaller scale, K of 0.05 and 0.01. In those scales, on large scale, this bispectrum from nonlinear gravity picks on the equilateral triangle. And on smaller scale, it picks on the folded triangle. And for the bispectrum induced by nonlinear galaxy bias, it also picks here and there. But really important thing for these four diagrams is that bispectrum is very, very small in this squeezed corner of triangular configuration. On the other hand, the non-Gaussian terms, I call FNL terms, they are small in all the other triangles, but then they are noticeable only in the squeezed corner of this bispectrum. That means, if you look at the galaxy bispectrum, it is a squeezed corner of this triangular configuration. That is the place that you want to look for the primordial signature. And then because all the other non-linear evolution terms picks the other triangles, but very small at the squeezed triangle, you can get this relatively clean signature of primordial non-Gaussianity from the squeezed triangle. That's why bispectrum is so good. And going beyond the primordial FNL, we can also search for the GNL and tau NL term. Those are the non-Gaussianity generated from the primordial 4-point functions. Again, they are very big on the squeezed corner and they're not so big in the other triangle. So that's again the same story. So you can measure the primordial non-Gaussianity by looking at the squeeze limit of galaxy bispectrum. Okay, let me change the gear a little bit. And then this is not conventional thing that people looked at in the galaxy power spectrum or bispectrum. So this is related to the Dirac delta function of this equation. So when you look at the power spectrum, we normally take the delta of k and delta of k prime, but k prime normally is taken as minus k. This is the result from the fact that this 2-point correlation function, delta of x and delta of x plus r, only depend on r, not x. This is in words, this is the assumption of statistical homogeneity. This assumption can be broken if you have certain set of primordial bispectrum. So I'm thinking of this 3-point function, the primordial delta and some spectator field that might exist in the early universe to give rise to this bispectrum. So this bispectrum does not break the statistical homogeneity globally because you have delta function here, right? But then this is a coupling, there's a proportion of the amplitude of spectator field, and then this epsilon is the polarization tensor that gives us some hint about nature of this spectator field. This bispectrum expression is exactly the same as this expression. Now, on top of this diagonal term means that on top of this k1 plus k2 equals 0 term, you do have some non-zero correlation even though k1 plus k2 is non-zero. In fact, k1 plus k2 is same as big K, that's the wave number of spectator field. Now, I'm thinking about the case where spectator field exists in the very early time but decayed away. But still, this 3-point correlation structure of spectator field is left in the galaxy density field. Then you might be able to detect this 3-point function and the existence of spectator field by looking at the off-diagonal correlation of galaxy density contrast. That is what I called, that's the work that I did with Markov-Minkowski, and that's what we call the fossil equation, because the spectator field itself decays away, but its 3-point imprint is remain there in the off-diagonal component of correlation function of galaxies. And where do you find this kind of correlation? This higher order interaction, right. So not linear theory, but if you go to beyond the linear theory, interaction between the primordial gravitational wave and density field can generate something like this correlation. And then I'm thinking of this as a way to detect the gravitational wave from the large-scale structure. I think we really had done the similar kind of work with Massey. So how do we expect that? So we start from this fossil equation. And then this fossil equation means that for a given K, big K mode of this fossil field, we can add up a whole bunch of different K1 and K2 that summed up to have K, right? And then your naive estimator will be just divide, this is summing up all of this delta K1, delta K2, and divide by this piece, right? But that's just naive estimator. And each term in this sum has a different variance. And then if you want to construct an optimal estimator from this kind of sum, what you can do is you do the inverse variance weight, right? That's the optimal estimator that we construct. Oh, by the way, what's cool about this estimator is that depending on the nature of this spectator field, HP, we'll have different polarization tensor. And this different polarization tensor will gives us different azimuthal dependence of this estimator. For spin 1 field, this one will be dependent proportional to cosine phi. Spin 2 field, cosine 2 phi. And if you had spin 3 field in the very early time of the universe, then we'll have cosine 3 phi, 4 phi, 5 phi. It goes on and on and on. And it's very easy to modify this type of estimator for different spins. So it's a generic way of searching for the higher spin field that might exist in the very early time. And we constructed optimal estimator, and we made a projection for the limit that we can detect the spectator field amplitude for the future galaxy survey. Like this 10 gigaparsec cube survey, I was thinking the HETDEX in my mind. And this line is this estimator. If the spectator field is gravitational wave, that's the line that we expect. So to detect this primordial gravitational wave, we want this line to be below. And for 10 gigaparsec cube survey, this means that we have to go all the way down to K of 10. So it's kind of hard to do. But if you have 200 gigaparsec cube scale survey, and then to detect the primordial gravitational wave, if this is really a gravitational wave, then you can just go down to K of, say, 4 or 5 to detect the gravitational wave. That might be possible in the future 200 centimeter surveys. But really, this spectator field does not have to be a gravitational wave. You can just generically use this estimator to search for some higher spin field or gravitational wave field or vector field that might exist in the early universe. So let me conclude here. So HETDEX survey will start at the end of this year, hopefully. And then this will be our first blind spectroscopic survey with a large volume. And we expect to have 0.8 Raman parameters. Using that, our primary goal is to detect the dark energy at high redshift. But then, other than that, we can also measure neutrino mass and curvature of universe and primordial power spectrum shape and primordial non-Gaussianity, as well as primordial gravitational wave or higher spin field that might exist in the early universe. Thank you.
Questions?
Okay.
I'm not quite sure if I understood quantitatively when you said that gravity and gravitational non-Gaussianity is primarily equilateral,
Right.
but zero at the squeeze. Now, the example you gave for decay of 0.01, and when you take the ratio, this little corner is Ks, is 10 to the minus 3 and below, right? Yeah.
Yeah.
You know, this in that corner, you have Ks less than 10 to the minus 3 parsecs, which is your horizon scale, right? So why is it meaningful to discuss that
No.
unobservable?
Right, this is just a two example, but if you just draw the same thing with a K1 of 0.1 or 0.2, you get the same thing. It's just two different example. So you can just do the K1 or 0.1, you get the same graph.
Well, then there's the other fact that because when you squeeze, if I have scales relative to the Ks instead, they just relabel my corners, we get the opposite conclusion. It's just a labeling artifact, it's not a physical process.
Labeling artifact means that you mean that this K number is too small that it will be.
No, it's the thing. So if you look at Cominelli and Pitot, 2008, whenever that was, 2010, when they go through that, they show that the gravitational effect, in fact, even in the ultra squeeze limit, is always equal in size and of order 5, and never smaller than the primordial.
Oh, I see, I see. You're saying that although this thing looks small, it's bigger than this.
Because how you label K, you know, you take ratio. When the K's are equal, that's a uniquely defined way of defining what your K is. When the K's are, you know, squeezed, you got to be a bit careful of what, you know. Let's say instead depends on, you know, there are two scales involved, and depending on which scale I label it relative to. So the objective question of whether or not how big an FNL's local gravity induces, Cominelli and Pitot found in asymptotes to 5 at infinite squeezing.
Asymptote to 5.
Yeah, so that's why I'm confused why your result is inconsistent and contrary to Pitot and Cominelli and Pitot and Benici.
I think I should look at that, and then we'll talk about it later. Yeah.
Is this in the galaxy by
Well, it's a CMB, but I mean, it's nonlinear. It's, you know, it's just a generic statement that the lensing and all these things that contribute. He includes the lensing, IW, all these things.
Right.
And I mean, unless there's something really subtle happening between galaxies and CMB, you know, I don't see how the galaxies can be so much smaller in the FNL than the CMB would be.
Right.
Smaller than 5. 5 is a pretty big number.
5, yeah, 5 is big number, yeah.
Any more questions?
Just have a wider question. What do you plan to do with all the data from this? Because you're going to have so many, IFU tends to produce very large data volumes. So
Right.
is it going to be open to the community for analysis? Or
Oh, yeah,
you
yeah.
throw some of it away if you...
Yeah, I think we get the funding from NSF,
If the fiber doesn't find something interesting, it'll just...
and NSF dictated us to release the data after 5 years of analyzing. I think we'll release part of data to the public. Yes, we'll do that.
Okay, just one more. Any more questions? Just one more question. So you talked about R, right? So in that plot that you showed where you overlap the Planck. So what does, because you talk about 21 centimeters when you talk about 0.22.
Oh.
So what is the ultimate limit of HETDEX itself? It didn't really, like, I don't think it
You mean
was on the plot.
which one? This one? This plot?
No, if you go all the way up to
All the way, okay.
black contour.
All right. Yeah.
Yeah. So this is way bigger than 0.22. No? So I don't know. Because you said there's some constraint that you expect, but
Oh yeah, but that's way up there. Yeah.
yeah, it's like 0.8 or something. What is it? Is there
So if you go there, I think reasonably
Oh, sorry.
we can expect to have like, you know. But this question is really tricky because for the normal cosmological analysis, we never use something beyond k of 0.3.
Right.
But then this one is an optimal correlation, and we don't expect anything from the normal analysis. So this thing, I think we can go smaller k max than the normal analysis. So in that case, this question depends on where do I stop here.
Yes.
But then this thing we may be ultimately limited by number density. So when the power spectrum is same as the Shan noise,
Right.
we don't go below that.
Sure.
Yeah. So I think probably it's around the 0.4. But this thing is still the order of magnitude.
Right.
So it should be like order 10, I guess.
I see. So it's very weak.
Yeah.